It is the second video of chapter 20 of the Crystal Clear Electronics video series. With Szabolcs, we would like to show you how voltage regulators and current limiter circuits work. In our previous video, we demonstrated the Zener diode voltage regulator, but the schematic didn't include the load.
Yes, we haven't dealt with this so far. In the schematic, we represent this load of some kind with a resistor. Because the Zener diode is added, the load marked with R2 will see a constant voltage. The current flowing through R1 will be shared by the diode D1 and the load R2. In the voltage range where the load does not influence the output voltage, the current flowing through R1 does not depend on the magnitude of load placed at R2. Such a circuit consumes the same amount of power regardless whether the load is on or off. This feature is both an advantage and a disadvantage. An advantage because the required current is always the same. A disadvantage because at low loads the efficiency is very poor. Another advantage is that it is difficult to imagine a simpler circuit as it consists of only two components. Now calculate the load at which the D1 Zener diode can provide a stable supply voltage. Because of Kirchhoff's first law, the sum of the currents flowing through D1 and R2 will flow through R1. If the voltage source marked with V1 has a voltage of 12 volts and the voltage of the D1 Zener diode is 6.2 volts, then the voltage across the resistor R1 will be 5.8 volts, so the current of R1 will be calculated as 5.8 volts divided by 1000 ohms is 5.8 milliamps. But let's examine this in practice. Here we have a lap supply. It will be the input, the V1 voltage source set to 12 volts. Now we will ask Marci to be so kind as to connect our multimeter in series with this power supply in the current measurement mode. So we are measuring the current consumption of this circuit. I will show you here that the R2 load would be this potentiometer. It has a resistance of 10 kΩ and now we're testing the circuit in a no-load condition. That means that I'm now turning it to the 10 kΩ position, so that's a very tiny current flowing through it. So you could say that there's no load on. You can clearly see the current consumption. Marci, can you read us what you see on the multimeter?
That's 5.8 milliamperes, which is what we calculated.
Well, that's very good. We can see the current draw without load. Let's look at what happens when I change the load. So now, I will turn this potentiometer and Marci will draw the conclusion. Now I'm turning the potentiometer and it's showing...
And this seems to remain stable.
That's right. So technically it means that the resistance of the load resistor R2 has changed. So its current has probably changed, but the voltage has remained the same. It is important to note that if R2 is chosen in the example circuit so that the current flowing through it is close to 5.8 milliamps, then the voltage will not be regulated anymore and the supply voltage of R2 will fall below 6.2 volts because in order for the voltage to remain stable, a current must flow through the diode. We can show this in the demonstration circuit we have built. We ask Marci to convert the current measurement into a voltage measurement. To do this, he has to disconnect the multimeter from the power supply. In the meantime, I'm putting the supply voltage back into the circuit. Very good, great! I turn the load to minimum and he switches the multimeter on to voltage measurement and connects the multimeter's test leads practically parallel to the diode, since that's also the output voltage of our stabilizing circuit. We want to see how this changes as the load changes. Well then, the voltage is already here. I start to increase the load, that is to reduce the resistance value of the R2 potentiometer. Then you can see that initially we started from 6.25 volts and then I turn it around and increase the load current, so to speak, and suddenly we see that the voltage starts to drop a little and suddenly we are rapidly out of this stable state. I can reduce it to 0 volts once the potentiometer practically goes into a short circuit state. Okay, but obviously if I reduce the load, we get the 6.2 volts back. Usually, this critical current value is not stated in the datasheet as a minimum current, but as a recommended current. If we look at the datasheet of our diode, it contains the Zener voltage at 3 different currents: 1 mA, 5 mA, and 20 mA. To keep the Zener voltage within the range given in the datasheet, at least 1 mA of current must be flowing through the diode. Also, look at the maximum current that can flow through the diode without destroying it. To calculate this, you need to read the maximum rating section of the datasheet. Since the datasheet is for the whole diode family, we will not find the maximum current, only the maximum power, but from that and the Zener voltage we can easily determine the current. 2 values are given for the maximal power. The one we need is the one with the standard circuit board material, which is 225 milliwatts. The other one is for when the diode is mounted on an aluminum heatsink. To determine the maximum current, we need to divide the power by the breakdown voltage of the Zener diode, that is 0.225 watts divided by 6.2 volts gives approximately 36 milliamps. Based on the datasheet, these values are valid for an ambient temperature of 25 degrees Celsius. Of course, we can determine how the maximum allowed power changes at higher temperatures based on the thermal conductivity. But a good rule of thumb is to only allow 50% of the maximum current through the Zener diode, which means 18 milliamps in this case. If the voltage of V1 is 12 volts, then the 5.8 milliamps current through R1 is well within the 18 milliamps limit, and with a 1 milliamp minimum current through D1, 4.8 milliamps is left for the load R2.
Let's suppose that V1 is a car battery, so the optimal voltage is 12 volt. Let's also calculate what happens at the boundary values of 9 volt and 14 volts.
If V1 is 14 volts, then we need to calculate whether the current flowing through R1 is less than the maximum allowed 18 milliamps. Based on previous calculations, 14 volts minus 6.2 volts divided by 1000 ohms is approximately 7.8 milliamps. So we are well within the limit. Now let's also calculate how much current is left for the load if the input voltage is 9 volts and we want to flow at least 1 milliamp through diode D1. This requires subtracting the breakdown voltage of 6.2 volts from the 9 volt and dividing it by 1000 ohm. That's roughly 2.8 milliamps. From this, of course, we must subtract the diode current, which must be at least 1 milliamps, so the maximum current to the load is 1.8 milliamps. What does this mean? It means that if we want our circuit to work anywhere between 9 volts and 14 volts, the load must consume less than 1.8 milliamps. Of course, we can improve this number by choosing a smaller R1, but then we would have to use a higher powered Zener diode too. This phenomenon, that the stabilizing effect disappears, can be easily represented here in our demo circuit. To do this, Marcell will take out the 10 kilo ohms load now, and I have a 1 kilo ohm load with me. It means that at 6.2 volts, approximately 6.2 milliamps will flow through this resistor, which is well above this limit of 1.8 milliamps. So, our expectation is that as the voltage decreases, the stabilizing effect disappears. So I'll give this to Marcell to put this load in. In the meantime, our lab supply is already set to 14 volts. I'm going to adjust it a little to make sure it's really 14, while Marcell puts the load in here. You can see that we've put in the load resistor and we're still at the stable 6.2 volts. However, if Marcell starts to reduce the voltage slowly, you can see that now, at 13 volts, the voltage is dropping. It's dropping very rapidly. Now we're around 11 volts and we are very far away from the 6.2 volts that we were expecting.
az, amit számítottunk, legalábbis
At least it's sure we consumed more than the calculated 1.8 milliamps, so the stabilizer can no longer operate reliably.
stabilizátor. Vegyük észre, hogy
You can see that this voltage regulation method wastes a lot of power
mint elpocsékol, hiszen
because a lot of energy is dissipated on R1 and D1.
és a D1-en disszipálódik el. Olyan áramkörrel
We need a circuit in which the maximum available load current doesn't change by this much if the input voltage changes. This is the problem solved by series voltage regulators.
a soros tápegységek.
Such circuits are, for example, linear power supplies which add transistors to the simple Zener diode. But we will talk about this in the next video. See you there! Bye.
Bye.